So in the last class, we started decoders, and these are some of the, it is not assignment, some of the problems that you can think of. We saw how to decide on the smaller number of decoders, and we did some example also. So this is what is the example that we just touched upon, and then we completed our last class. So number one, you have to implement this given function using a decoder, right? They did not mention much. So since you are having your minterms till 7, you have to obviously use a 3x8 decoder because you will have 8 output lines here. So if you implement it, so this is how you implement, right? So this is your uh, number 4 output, 6 output, and 7 output. 4, 6, 7 ORed together. You will be able to implement this function f, a, b, c. But is it a viable option? For this particular case, it might be viable. Why? Because this is just a simple 3:8 decoder only. Say for example, you want to implement 5x32 decoder, right? So this is a huge, large decoder. You want to implement 6x64 decoder, it is still a much larger decoders. And you have to specially design these kind of ICs. Why? Because this will, your IC now, it will take 6 inputs here, right? 6 inputs here, and then it has to take 64 outputs. So 64 plus 6, how many? 70 pins you will be having in your ICs, which is not a feasible option. So hence it is always, and at the same time, to design such kind of ICs with so many number of pins, it is not a viable option, and at the same time they will be much costlier also, and at the same time they will be slower. Because you think of, you will there will be the AND gates that you have inside these decoders will be having 7 inputs here, right? 6 from the actual input and 1 from the enable signal. So 7 inputs. So each AND gate will be a 7 input AND gate. If you want how 7 input AND gate, this is a very simple 2x4 decoder. So which means each AND gate here is having 3 inputs including the enable signal, right? So 3, 3, 3. So if you are having a 6:64 decoder, then you will be having 7 different inputs. Okay, so hence we said that this is not a viable option to always go in for larger decoder ICs. Now, how do you implement this then? You can always implement this using the smaller decoders. Now, yesterday we just saw how to identify the number of smaller decoders. So always look at the output side. If you want to use 2x4 decoders, then how many 2x4 decoders you want? You need two 2x4 decoders if you want to implement this 3:8 decoder. But at the same time, so you will have two 2x4 decoder. So outputs are fine. 4 outputs will be here, 4 outputs will be here. But only 2 inputs will be here and 2 inputs will be here. What about the third input? This third input, so for the third input, you will have to again, because first you have to select the decoder chips, right? So you need one more decoder, which will enable, so how many decoders you have? You have 2 decoders to be selected. So 2 output decoder must be there. If it is 2 output decoder, then you will have 1 input. So this will be the 2 outputs B and C, and this will be the third input A. So A, B and C will be the 3 inputs here. So what I am trying to say here is, in addition to 2 2:4 decoder, you will require one more 1:2 decoder to select these decoders. Okay, so that also you must keep in mind. Now let us come to the implementation part. Yes, how many decoders you need? You need two 2x4 decoders, and one is to the decoder to select the two decoders here. Now let us see how to implement this. I've already said always first draw the 2x4 decoder, the larger ones. So you have 2x4 decoder. You have two signals here. So BC and BC. So out of the three input signal A, B and C from this function, we are using B and C. Okay. So we are using B and C as the input to these 2x4 decoders. So if it is 2x4, what will be the, so this function ranging from 0 to 7. Am I right? So 8 inputs will be there. So 0 to 3 will be the outputs of the first decoder, and 4 to 7 will be the outputs of the second decoder. Now you will be having enable signals also. So you use 1:2 decoder. So one input will be A input and outputs are going to be 0 and 1. So, and the enable signal will be 1 here because we can always enable it. Whenever A is 0, right? So this first decoder will be selected, which means that A, B and C, whenever A is 0, 0, BC can take values 0, 0. If it is 0, 0, then this output is selected. 0, 1, this output is selected. 0, 2, this 0, 1, 1, 0. This output is selected. 1, 1, this output is selected. When A is 1, let me write here, okay, because I don't have space. If A is 1, then this will be disabled and this will be enabled. It can take again 0, 0, then this output is selected. 1, 0, 0, please see here. And then if it is 1, 0, 1, so this is 1, 0, 1 corresponds to 5. So the fifth input, fifth output. 1, 1, 0, sixth output. 1, 1, 1, seventh output is selected. So this is how we work. Now coming back to the problem. Coming back to the problem. What is the function that they have asked us to implement? It is f of a comma b comma c is equal to the minterms 4 comma 6 comma 7. Am I right? Okay. So now we have created the setup. Now we have to complete this implementation of the minterms. So where is 4? 4 is here. Where is 5? 6? 6 is here. And 7. Right? So, and we put an OR gate, and this is what is the function f of a comma b comma c equal to minterms 4 comma 6 comma 7. One thing that we observe here is we have not used the outputs of any of the first decoder at all. Then immediately the question comes, unnecessarily if you are not using any outputs here, then do you really need this decoder? You do not require this decoder. If that is the case, then how do you simplify the circuit? Please note everything is related to cost. When something is not useful, then why do you spend money on that, right? Then how do you simplify this particular circuit? So which means that we do not want this zero selection at all here, right? So what you can do, just remove this and open the zero output here. So we can save a decoder here. So reducing the circuit here, we are not at all using the zero selection line, just to give it as open. And we are using only the one output. And for the one output, please look at the, this is actually 4, 5 is here, 6 and 7. Okay, now all you need to look at the combination here. This is 1. Okay, this is going to take 4 possible combinations. So BC will take 4 possible combinations, 0, 0, 0, 1, 1, 0 and 1, 1 combination. So along with this one, you have to combine and then get the output. Right? So any doubt in this implementation? Okay, now let's take another example. This particular example here, I think, yeah, this is a different example. We are using the 4 1 cross 2, the same example, yeah. So the same function f of a comma b comma c, the minterms are 4, 6 and 7. Now you have to implement the same thing using 4. 1:2 decoders and 2:4 decoders, which means that normally this can be implemented using 3:8. Instead of 2:4 decoder, if I use 1:2 decoder, then how many decoders I want? Because 2 outputs are here and 8 outputs are required. So I will need 4 number of 1:2 decoder. Now to select this 4 decoders here, please see here that these 4 decoders needs to be selected. So then I need 2 cross 4 decoder, one number of 2:4 decoders. If that is the case, for this one input, inputs from this particular function, I can use C for this function and I can use AB for this 2:4 decoder. That is what has been done here. If I use C as the function, please note this is just 1 cross 2 decoder. Only 2 options are available. So 0 is one option and 1 is another option. So likewise, only C input is here, 0 and 1. See it. So you have now write the possible output. So this is 0. This corresponds to 0, 1, 2, 3, 4, 5, 6, and 7. And I must always combine this C input along with AB input here. So if AB can take, what are the values it can take? It can take 0, 0. If say for example, I want 4 function, right? So 4 means 4 corresponds to 1, 0, 0, which means that AB must be 0 and C must be 0. So when AB is 0, this will be selected. This particular line will be selected. No, AB. Yes. Okay, I'm sorry. Yeah, correct. This will not be selected. When AB is 0, sorry, when AB is 1, 0, right? The third line is selected. Which is the third line? This line will be selected. But please note, all when C is 0 here, when C is 0, all these corresponding 0 output will be available for the outputs. Available for the output. But based on the AB signal here, right? Only the third line will be selected and only this decoder will be selected and you will have high signal across this output only. When it is 1, 0, 0. When it is 1, 1, 0, then which decoder will be selected? This decoder will be selected. And when it is 1, 1, 0, this output will be available. When it is 1, 1, 1, then this output will be available. This is how the decoder works. Again, this can be further simplified, right? How you can simplify? Because we are not using any of these outputs, you just ignore this decoder. So you will be saving some cost here. So 0, 0 and 0, 1, we are not going to use. We are going to use only the 1, 0 and 1, 1 outputs here, and then we can just use 2 decoders only. So by this way, you can further simplify the circuits. Any doubts here? Okay, let's move further. Now you have to implement this one. Now a function f of ABC equal to 0, 1, 2, 3, 6. There are 2 ways to implement. Either using a 3 cross 8 decoder, or you can use 2 cross 4 decoders and 1 cross 2 decoder, one number of 1 cross 2 decoder. So let us implement this. So first I have always said, try to draw the 2 cross 4 decoders. If A, B, C are the inputs, last 2 inputs will be corresponding to the 2 cross 4 decoders. B and C, everything will be repeating. 2 cross 4 decoders. And 1 cross 2 decoder, enable signal will be 1 here. So what are the outputs here? It is 0, 1, 2, 3, 6. So 0 corresponds to this line, 1 corresponds to this, 2 corresponds to this, and 3 corresponds to this. 6 corresponds to what? This is 4th output, 5th output, and 6th output. So this corresponds to this one. But if you see here, this particular decoder, all the outputs we are using. If we are using all the outputs, then can we minimize this? Yes, we can minimize this. What we can do is you just remove this particular decoder. That is, whenever your A value is 0, it means that you will be having an output here. Am I right? So which means that you, instead of having this, you can directly connect this to a OR gate here. Okay, so if you want a theoretical explanation to this, what we can do here is, what does all these lines corresponds to? This line corresponds to, let us assume that this is, just for the sake of simplification here, instead of BC, I've used A bar B bar, or if you want, you can use B bar C bar, right? 0 0 corresponds to what? 0 0 corresponds to B bar C bar. 0 1 corresponds to B bar C, right? So they are all ORed together only, right? They are all ORed together. So it is B bar C plus 1 0 corresponds to BC bar plus 1 1 corresponds to BC. You can simplify this. Take B bar outside from this first two. So I have C bar plus C. Take B outside from this. I have again C plus C bar. What is this C plus C bar? This will be 1 plus B multiplied by 1. So again, you can take, what is B bar plus B equal to? B bar plus B is equal to 1, which means that the sum of all these inputs will be 1. So instead of having a separate decoder, just connect your select signal directly to your OR gate. Whenever this is going to be 0, your output is going to be available. So that is the simplification here, right? So you can again save one 2 cross 4 decoder by just directly connecting the 0 to your output. Right? So this is one way of implementing. Any doubts here? Okay, let's move on with another example. See, every example is unique, so that is why I am covering every example here. So now you have to implement this function. So how do you implement? There are again two ways, either 3 cross 8 decoder or two 2 cross 4 decoders, and to select this two, I need 1 cross 2 decoder. How many? One number of 1 cross 2 decoder. So let us implement this. First, let us draw the two 2 cross 4 decoders. So we have two 2 cross 4 decoders here, and this will be identical. Okay, so this is decoder number 1, this is decoder number 2. They will be completely identical. And then to select this, please note this is your enable signal. This is your enable signal. When it is 0, your first decoder is selected. When it is 1, your second decoder is selected. And A will be, so the first decoder will be a 1 cross 2 decoder to select these two decoders. Always you must look at the combination of these inputs only. Okay, A, B, C. Similarly, A, B, C. Okay, now what are the min terms here? We have here 0, 3, 4, 7. So 0 corresponds to 1, 0, 0, 0. 3 corresponds to 0, 1, 1. 4 corresponds to 1, 0, 0. 7 corresponds to 1, 1, 1. So I've always said that look from the combined inputs only. So when it is 0, 0, 0, when this is 0, obviously this line will be selected. And when these two are zeros, this line will be selected, right? So this corresponds to 0 line, this corresponds to 3 line, this corresponds to 4, and this corresponds to 7. Okay, now again there is a peculiar case here. You see a same pattern here. In two decoders, the first line and the last line output lines are taken as your output. Similarly, in the second decoder also, first and third lines are selected. Whenever you are having such a kind of a pattern across different decoders, what you can do is you can again remove one kind of a decoder, and you can just create an OR function, something like this. Something like an OR function like this. Okay, what is this particular OR function? That is, in both the decoders, whether your select signal is 0 or 1, right? So we are going to use the first and the last output only. So you can always simplify. So maybe let me read this. If we have same pattern of outputs from two or more decoders at second level, we may keep one decoder and use an OR gate on complementary outputs from first level decoders. Okay, so you can see here that A is the output and this is an OR gate here, and enable signal is always 1. So whether it is 0 or when it is 1 here, right? So when it is 0, obviously this line will be high. Okay, and then again this the first line will be selected and still the function will work. Now, can you still further simplify this? Yes, you can simplify this. Why? How? Because we know we are ORing it only, right? This line corresponds to A bar. This line corresponds to A. So if you are ORing this, what is A plus A bar? What will be the output here? This is equal to 1 here. So this is 1. So simply you remove that particular input and give an enable high, always enable high input here. Still the same function can be implemented here also. That is f of a comma b comma c. Still it will work in terms of 0, 3, 4 and 7. Still this particular function will work. Provided the only thing is it is f of a value is equal to 1 comma b comma c. Right? Still the function is going to work. So any doubt here? Okay. Now again you are saying multiple peculiar decoders here. Let's take another peculiar example. So now it is a 4 input for a variable minterm function. So these are the functions given. Purposefully, let us find out the what are the ways to implement this, since this is a 4 variable function. So 4 inputs are there. So 4 cross 16 decoder you can use. Or if you are using 3:8 decoders, how many 3:8 decoders? I need 2 3:8 decoders. If I am using 2 cross 4 decoder, then I will be using 4 2 cross 4 decoders. So if I am using 4 cross, if I am using 4 2 cross 4 decoders, then I will be needing to select this 4. I will be needing one more 2 cross 4 decoder, right? One more 2 cross 4 decoder to select these 4 signals. If I am using 3 cross 8 decoder to select this, I need 1:2 decoder, because these 2 outputs will be used to select these 2 decoders. Now let me take the second option. Okay, this also you can take, but we are definitely not going to do this. We are going to use the second one, which means we are going to take 2 3 cross 8 decoders and one 1 cross 2 decoder. Now let us look at the outputs. So how I am going to classify my outputs. So A and B, the first two will be used for my 1 cross. Okay, this is 1 cross 2, right? So yeah. Okay, I can use this particular pattern. Okay, so directly I've been given I'm giving you the answer. Never mind. So this is how we are going to implement this. Again, why this particular pattern has been implemented is from the minterms itself. You see it is 0 1 2 3 4, which means that my first 3 cross 8 decoder here, let me erase this. My first 3 cross 8 decoder here will have outputs 0 1 2 3, right? So which means that I can use an OR gate here, right? So I can use an OR gate from my first selection line 0. Okay, so this particular line corresponds to the first decoder part. So I have used OR, which will cover from 0 to 3. This 0 will cover from 0 to 3. Now what are the next outputs? I am having 4, 5, 12 and 13. Okay, now if you look at the pattern here, 4 corresponds to, okay, look at the binary values here. This is 0 1 0 1. 12 corresponds to 1100, 13 corresponds to 1101. So please note we have split our inputs as 0 1 here. So these two corresponds to AB inputs, which means 1 1 also corresponds to AB inputs, 1 1 also corresponds to AB inputs. 0 1 corresponds to CD input, this corresponds to CD output, CD inputs. So here 4 in the second decoder corresponds to 0 1 0 1, right? When it is 0 1, and at the same time we are ORing it, right? So this corresponds to 1 1. This is 0 0 0 1 1 0 and 1 1. So 0 0 we are anyway ORing it with our final output. So this will take care of 0 2 3. Now we need 0 1 1 0. So 0 1 we are ORing with the 1 1 output here. So we are ORing with the 1 1 fourth decoder output. We are ORing it, and then we are connecting it to what are the outputs we need? We need 0 1 0 0 0 1. So we need 0 0 0 1. So there are two 0 1s here. So we can use only one decoder because the first two parts will be selected from the first decoder itself. Okay, so this is how you can simply implement. If you want, you can create a truth table and then you understand. Maybe quickly I can tell you here. So what are the four variable map, four variables input combinations? These are the four variable input combinations. That is 0 0 0 0 0 0 0 1 likewise. We all know that if you want to implement for 16 variable function, you need how many decoders? You need two 3x8 decoders, or in fact, this is how 2x4 decoders. Okay, now we are using only two 2x4 decoder. So the first four inputs will be taken care by the first decoder. Second to this particular thing will be taken care by the second decoder, and these things will be taken care by the third, and the last four will be taken care by the fourth decoder. So now what we have used is, so in order to implement these functions, we do not require any decoder because all the inputs are here. So this takes care of the first decoder. Now the second decoder, we have only one function here. So one function, what is the output here? It is 0 1 and 0 1. So we are going to use this one for the second decoder. Are we using the third output combination? We are not using the third output combination. So we do not want any third decoder. Hence, there is no output coming here, which will take care of the third decoder. For the fourth decoder, this is the fourth decoder output we are taking as the output. So which means we are utilizing the first two input combinations only here, 0 1 and 1 1. And we are ORing it, and then with the C and D outputs, we are configuring our decoders for the last two inputs. So 0 1 here. Here also we are having 0 1s because the 0 1 has already been taken care. So we connect this and then create a simplified 2x4 decoders. Though the last one is slightly, it is not complicated, but if you go step by step, you can implement this. How step by step? That is, first create the four 2x4 decoders. Okay. So when you create first four 2x4 decoder, automatically this will simplify to this particular circuit if you follow the previous examples that we have done. Okay. So any doubt in this decoders? Okay. Now let's move on to encoders. Now encoder is completely the reverse of a decoder. What is the reverse of a decoder? Decoder had n number of inputs and 2 power n number of outputs. If we have two inputs, then we have four outputs. If we have three inputs, 2 power 3, which is 8 outputs. If we have four inputs, 2 power 4, 16 outputs. 2 cross 4 decoders. Sorry, n cross 2 power n decoders. Reverse means what? We will have four inputs here and two outputs. We will have 8 inputs here and three outputs. We will have 16 inputs and four outputs. Whereas these encoders are used. If you are using a decoder, then there must be a device to encode also. So, for example, you consider octal to binary encoder. Binary to octal will be a decoder because the number of inputs for a binary is large. So this, yeah. So this can be an octal to binary encoder, your input is going to be octal and your output is going to be binary. So for octal, let us consider a 3-bit binary output. So if it is 3 bits, so n will be 3. So how many number of inputs will be there? 2 power n, 8 input combinations will be there. So this will be an 8 cross 3 encoder. Let's make a truth table for this. If you make a truth table, please note here that this is a 8 cross 3 encode. This is 8 cross 3 encoder. So what are the 8 inputs? Let us assume. So before that, let me draw a block diagram. How this is going to look like? This will look like something like this. 0, 1, 2, 3, 4, 5, 6, 7, 7, and let me write here 8. Okay. How many outputs will be here? This is 8 cross 3 encoder. There will be 3 outputs. 1 output, 2 output, and 3 output. Now, what is the function? If I want to convert from octal to binary. Okay. If I want to convert from octal to binary, say for example, what is the octal number of 6? The octal number of 6 is going to be 1, 1, 0. Am I right? So if I'm giving 6 as, if I'm giving 1 across my 6, then the output that I must get must be 1, 1, 0. If I'm giving 2, then my output must be equal to 0, 1, 0. So if I'm giving a 6, so 6 will be 0 now. My 2 will be 1 here. Then my output will be now 0, 1, 0. This is what is the function of an encoder is. So what will be the truth table now? Your truth table now, what are the inputs? D0 to D7, right? So why D? Because normally these encoders are used for data transfers. So hence data 0, data bit 1, data bit 2 likewise. So if D0 is 1, then your output will be 0, 0, 0. Your D1 is 1, your output will be 0, 0, 1. When your output is, likewise, when it is D5, 5 corresponds to 101, so it is 101. Likewise. So now if you look at the Boolean expression for these output functions, for X if you write, these are the ones we are having. Let me change the color. These are the ones we have. So what is the Boolean expression for this? This one corresponds to D4, this one corresponds to D5, this corresponds to D6, and this corresponds to D7, which means that X is equal to D4 plus D5 plus D6 plus D7. Similarly, Y corresponds to D2 plus D3 plus D6 plus D7, D2 plus D3 plus D6 plus D7. Similarly, the Z corresponds to 1, 3, 5, 7. Now, if you implement this using the gates, AOI gates, this is how it will look like. I'll zoom out so that you can see the expression and yeah. I want this to go. Okay, I think now you can see. Oh, I want this to go. Okay, forget about it. Okay, so now D0, are we using D0 here? We are not using D0. So this is just an input line, but without any connection. X will have D4, 5, 6, 7. So X have D4, 5, 6, and 7, right? So this corresponds to D4, 5, 6, and 7. You can see you can trace the paths. So this corresponds to D4, this corresponds to D5, this corresponds to D6, and this corresponds to D7. Similarly, Y corresponds to 2, 3, 6, 7. So the Y corresponds to 2 here, 3, 6, and 7. Okay, and the last one corresponds to 1, 3, 5, 7, right? So 1 here, 3 here, 5 and 7. Right? So this is how the internal circuit level is. Please see here the number of input lines. So we need a 4 input OR gate. We need a 4 input OR gate, 4 input OR gate. All these can be just implemented using OR gate. But there are problems here. What is the problem? What if I don't give any inputs here, which means that there is no inputs at all. Everything is 0. When everything is 0, what will be the output? Output will be 0, 0, 0 because I have not given any inputs here. But 0, 0, 0 corresponds to which output? 0, 0, 0 output corresponds to D0 equal to 1. This is a problem, right? So there is another problem here. What is another problem? Say for example, if uh, two inputs, say 3 and 6, let us take the example, yeah. So, okay, so let me go through this. There are two design issues in the encoder part. There are two ambiguities associated with the design. Let me go back to the second one first and then come back. An output with all zeros is generated when all the inputs are zeros. This output is same as that when D0 equal to 1. Okay, so this is the problem. Now the first ambiguity is when only one input can be active for this encoder, but if two inputs are active simultaneously, then the output that will be produced will be an unidentified combination. What does this mean is, let us consider, let me erase this. I can't erase. Okay. All right. So now, say for example, 3 and 6 are active. Okay. So which means in this, my 3 is also having 1 and 6 is also having 1. Let us assume that this is 3 and this is 6. My 3 is also 1 and 6 is also 1. So if 3 is 1, this will be 1. This is an OR gate only, right? This I will have 1 here. So when 6 is 1, please see here that 6, this will be 1 merit. So this is going to be 1. This is already 1. And because this 3 is 1, there will be an OR gate here. This will also be 1. So if my 3 is my input, what is my output that I desire? I desire to have 0, 1, 1 as my output. If 6 is the input, I would like to have 1, 1, 0 as my output. But what is the output that you are getting here? The output that you are getting here is 1, 1, 1, which is not corresponding to 3 and which is not corresponding to 6 also, right? So how do you solve this problem? How do you solve this particular problem is, you can create some kind of a priority. What do you mean by priority is, if say D3 is high and at the same time D6 is also enabled or high, then always give priority to the larger number, which means when 3 and 6 are active, give priority to 6, which means you will get the output 110 only and not 011. This priority can be easily made in the uh, digital circuit by special circuits called as priority encoders. Okay, there are circuits called as priority encoder. What is this priority encoder will do is, when you have multiple inputs, then only one will have a priority, which means that the larger one will have a priority than the smaller ones. Any doubt here? There is a circuit with a priority encoder. We will see that maybe later. Any doubts here? Okay. Now let's move on to the third kind of combinational circuit, which is called as a multiplexer circuit. Multiplexer you must have come across. In olden days, what happens is, when people are trying to make that is in 1980s, where the telephones were primarily based on, the connections were primarily based on trunk calls. You know what is a trunk call is? Trunk call in the sense, in olden days, if I want to dial somebody, say digital electronics. Okay, so let me use this page. Okay, so if there will be a office, say if my place is in Greater Noida, right, there will be a Greater Noida office. Okay, and this from Greater Noida office, there will be hundreds of houses which will be connected. Okay, and say for example, I want to make a call. What I will do is I will create a trunk call. That is, the person sitting in the office will pick up my call. I will say that I want to connect it to somebody. I mean, say for example, Ghaziabad is another place. This will have a code number. I will say that I want to connect this phone number. So this particular person who is sitting at the office, they will create a trunk call. There will be multiple lines that will be going, right? There will be multiple lines that will be going. So this will be to some city, this will be to some city, and the numbers here. They will create, they will connect me, they will connect my line to this particular line. And the person sitting here, further on identifying my number, they will connect it to this particular line, right? And how this particular process of connecting and switching is taking place is, this particular process is a combination of a multiplexer combination and a demultiplexer combination. What is a multiplexer is, from many inputs, I am getting connected to one output here, right? This is called as the multiplexer connection. What is a demultiplexer connection is, from one input, this particular person is trying to connect it to one output of many outputs. Am I right? So this is called as the demultiplexer connection. So this end we are having a multiplexer connection. This end we are having a demultiplexer connection. So which means that this person who is sitting here acts as a selector, right? Instead of a person, let me call him as a selector here. Similarly, this person here, this person, instead of a person, I am going to call him again as a selector. What is the function of this particular selector? He will guide me, he will create a connection from multiple inputs, that is n number of inputs, to one output, right? One output here. This particular person will connect from one output to n number of outputs based on the value of this particular select lines. Now let us go technically into the actual subject and then let us understand. This is the primary principle and the application also. So what does a multiplexing means? Multiplexing means transmitting a large number of information over a small number of channels. Right, as I mentioned here, over a large number of channels to a smaller number of channels here. So a digital multiplexer is a combinational circuit, right, which selects the binary information from one of many input lines and directs it to the single output line. So these selections, so these selections of a particular input line is controlled by a selector line, and this is called as the data selector. Okay, now how does it look like? It looks like this. It looks like this. So this is either somebody will use a box like this. Some authors will use a box like this to represent a multiplexer. Somebody will use a trapezoidal function, something like this, as a multiplexer. Anything is okay. Why trapezoidal is because the number of output here is just only one, right? So that is the reason. Somebody will use a triangle also. Right? These are also used to implement a multiplexer. Okay. So here you will have 2 power n number of inputs and only one output here, which means that how do I represent a multiplexer? If say for example, n is equal to 2, I will represent this multiplexer as a 2 cross 1 multiplexer. And how these input combinations are there? N represents the number of select lines. If say for example n is equal to 2, then I will have 4 input lines here. Only 4 input lines can be selected. If my select lines are 3, then I can have 2 power 3, which is 8 input lines can be directed to one output line. So now the relationship now here is between the select lines and your input lines only. Output line is just directing. Okay, so the select lines will play a crucial role in selecting the inputs and carrying forward to the output. Now let us look at the function here. What is the function? Say for example, I am trying to call somebody in Ghaziabad, right? Let me assume that my phone number is 0. If say I can call somebody just randomly, say Sashank is here. So Sashank's phone number is 1 and he is also trying to make a call. And somebody else, Pradyumn is here. Pradyumn is also trying to create a call. Let us assume that his number is say, the last number say, let us assume that 8, right? And there are 3 select lines here. Based on these value of this select line, because let us assume that I am senior, okay? So if my select line is 0, 0, 0, I will get the priority to speak first to my desired destination. If say for example, Pradyumn is senior as per the date of birth, maybe some just random criteria. So if my select line is 111, his number, let us assume 7, then he will get the next priority after me. Likewise, the select lines will decide which input will go to the output. I hope I have made it clear. Okay. Now let us take a very simple example of a 2 cross 1 multiplexer. I think we will take this example and then we will wind up before we move on to the 4 cross 1 multiplexer. Now, when I say 2 cross 1 multiplexer, number of inputs are going to be 2. Number of outputs, obviously, it's going to be only one output line, right? So this is going to be fixed. Now, how many select lines will be there? So what 2 power n is equal to 2? 2 power 1 is equal to 2. Am I right? So which means that n is equal to 1. The number of select lines will be equal to 1 here. And how does the block diagram will look like is, I have 2 inputs here, input 0 and input 1. It is a 2 cross 1 multiplexer and one select line. S is my select line and one output line. So when my S is equal to 0, my output will be equal to, that is Y will be equal to I0. When my S is equal to 1, then my output Y will be equal to I1. How do you implement this using gates? How do you implement using this gates is, though I have a circuit, it will not look nice. If you directly look at this circuit, I will draw here, then you will understand. So I'm going to have AND gates here, 2 AND gates. I will have I0 as one of my inputs and I1 will be another output. I'm having a select line, right? When my select line is 0, which means that a low signal here. So I'm creating a NOT gate. This will become S bar. This will become S bar. So when my S is 0, then this will be enabled. When my S is 0, what happens? This S bar will be 1 here. And please see here that all my inputs are available, but which takes the priority is decided upon the select lines. So I0 is also 1, I1 is also 1. So since my S is 0, this line will be 1 and my Y output will be equal to my Y output. Let us OR it. Okay. My Y output will be equal to 1. If my S is equal to 1 here, if this is 1, what happens? This will be 0, this will be disabled and this will be enabled. This will be enabled here and I will get my output. So which means that I1 now will be connected to Y1 when S is equal to 1. When S is equal to 0, then I0 gets connected to Y1. So this is how the block diagram of a 2x1 multiplexer will look like. Maybe we'll cover 4x1 also so that your visualization will be slightly better. When I say 4x1 multiplexer, number of inputs are going to be 4 and number of outputs are going to be 1. What is equal to what? N is equal to 4. So n to power 2 is equal to 4, which means number of select lines will be equal to 2. So I have 4 inputs here. So I0 to I3 are my 4 inputs. So the number of select lines are going to be 2. So hence my select lines are going to be S1 and S0 and my one output which is equal to Y. How does the block diagram will look like? I will have 4 AND gates here. 4 AND gates here. And all my 4 AND gates will have my inputs I0, I1, I2 and I3. And all this will be ORed together to have an OR gate. So this is going to be my Y. Now these input line, the selection of these input lines are dependent on my select lines. So this is my S1 and if this is my S0, sorry I don't have space. When it is 0, 0, this line will be selected, okay? When it is 0, 1, this will be selected. When it is 1, 0, this will be selected and 1, 1, I3 will be selected. So I'm creating what is 0, 0, S0. So this will be S1 bar and this will be S0 bar, S0 bar. What is 0, 1? 0 corresponds to this one and 1 corresponds to this line, right? So you see in this diagram, it will be clear. So this corresponds to S1, S1 is this line and S0 is this line. This corresponds to S0, S1. So this is your S0 line and this is your S1 bar line. And last corresponds to S0, S1. This corresponds to 1 and this corresponds to 1, right? So this is how your 4x1 multiplexer will look like. And okay, I think we will look at the truth table and the Boolean expression. Yeah, maybe 2 minutes I'll cover. Yeah. Okay. Now if you look at the truth table here, these are the inputs, right? I0, I1, I2, they are already available and they have their own bits, data bits. D0, D1, D2 is available across these. So D0 is available across I0s. D1s are available across I1. Data 2s are available across input 2. D3s are available across I3. So when it is 0, 0, your output will have D0. When it is 0, 1, your output will have D1. When it is 1, 0, your output will have D2. When it is 1, 1, your output will have D3. In short, we can just simply write that though this is a truth table, this is called as a functional table. When it is 0, 0, your output is equal to I0. When it is 0, 1, your output is equal to I1. When it is 1, 0, it is I2 and I3 for 1, 1. Now, how do you write the Boolean expression for this? Boolean expression now can be just simply written as y is equal to, I have written here, it is I0 multiplied by, this corresponds to S0 bar, S1 bar, S0 bar, S1 bar, I1 multiplied by S0 bar, S1, I2 multiplied by S0, S1 bar, and I3 multiplied by S0, S1. Right? So the output of your multiplexer will be the SOP of these things. Okay. So this is how you write the Boolean expression for a 4x1 multiplexer. Any doubts here? Okay. All right. So we'll continue with a lot of examples with the multiplexers also maybe in the next class. Okay. So thank you so much.